In this video, we will study the Twocavity Klystron Amplifier, presented by Professor Gottapu Sasibhushan Rao. We will understand its principle of operation, the role of velocity modulation and electron bunching, the Applegate diagram, and finally a gate examination problem. The main idea is simple. An RF input signal changes the electron velocities, the electrons form bunches, and these bunches transfer energy to produce an amplified microwave output. Microwave tubes are broadly classified into two categories. The first is the O-type, or linear beam tube. Here, the electric field and the magnetic focusing field are approximately parallel. The second is the M-type, or cross-field tube, where the electric and magnetic fields are perpendicular. The klystron and reflex klystron belong to the O-type category. So, a two-cavity klystron is essentially a linear beam microwave amplifier. Now let us follow the electron beam from left to right in the figure. The electron gun first produces the electron beam. The beam is accelerated by the DC beam voltage. The electrons then enter the first resonator, called the buncher cavity. The RF input signal is applied to this cavity. Because the RF field varies with time, different electrons experience different electric fields. Some electrons are accelerated, some are decelerated, and some pass almost without any change in velocity. This process is called velocity modulation. After leaving the buncher cavity, the electrons enter the drift space. There is no RF input applied in this region. However, because the electrons now have different velocities, the faster electrons gradually catch up with the slower electrons. Hence, the electrons begin to form groups or bunches. This converts velocity modulation into density modulation or electron bunching. The bunches then enter the second resonator, called the catcher cavity. At the correct RF phase, the bunches are decelerated. The kinetic energy lost by the electron bunches is transferred to the RF field in the catcher cavity. Therefore, the RF signal becomes amplified. Finally, the amplified microwave output is taken from the catcher cavity, and the remaining electrons are absorbed by the collector. So the complete process can be remembered as RF inputs velocity modulation, electron bunching, energy transfer, amplified RF output. For the equation shown on the slide, you need not read every symbol. Simply say, this relation gives the average velocity of electrons accelerated by the DC beam voltage. As the beam voltage increases, the electron velocity also increases. That is much more natural for a video. Now we come to the Applegate diagram. This is a distance versus time representation of electron motion in the drift space. Look first at the RF voltage waveform near the buncher cavity. Depending on the instant at which an electron crosses the cavity gap, it experiences a different RF field. Therefore, three representative electrons are shown. The slower electron has a velocity less than the normal beam velocity. The reference electron moves approximately with the normal beam velocity. The faster electron has a velocity greater than the normal beam velocity. Now observe the straight electron trajectories. The faster electron gradually approaches the reference and slower electrons. The slower electron lags behind. As the electrons move through the drift space, these trajectories converge. This convergence represents the formation of an electron bunch. The bunch is ideally formed near the catcher cavity so that maximum energy can be transferred to the output RF field. The RF equation shown on the slide simply represents the sinusoidal RF voltage applied across the buncher gap. You can narrate it as the RF gap voltage varies sinusoidally with time. Because electrons cross the gap at different phases of this waveform, they receive different changes in velocity. For the velocity modulation equation, say, this equation shows that the final electron velocity is slightly higher or lower than the original beam velocity, depending on the RF phase at which the electron crosses the gap. There is no need to read the complete mathematical expression aloud. A good closing line for this slide is different velocities, different trajectories, trajectory convergence, electron bunching. Now let us apply the same concept to a gate-type numerical problem. The problem gives the operating frequency, the distance between the two cavities, and the beam voltage. we are asked to determine two quantities. First, the DC electron velocity, and second, the transit time between the two cavities. The first step is to calculate the electron velocity from the beam voltage. Instead of reading the complete equation, say, we use the standard relation between accelerating voltage and electron velocity. After substituting the given beam voltage, we obtain the DC electron velocity. Next, the transit time is simply distance traveled divided by electron velocity. So we divide the cavity spacing by the calculated electron velocity. This gives the time taken by the electron beam to travel from the buncher cavity to the catcher cavity. The important point is that this transit time determines the RF phase at which the bunch reaches the catcher cavity. For efficient amplification, the electron bunch must arrive at a phase where it gives energy to the catcher cavity.